Hello guys, today we're going to talk about inductance. We're going to discuss the properties of inductance in an alternating current circuit. We're going to discuss inductive reactance. We're going to compute some values of inductive reactance and inductance. We're going to discuss the relationship of voltage and current in a pure inductive circuit. We're going to discuss reactive power, or VARs, VAR, and we're going to determine Q of a coil. Q means the quality of a coil when it comes to inductance. Inductance is one of the primary types of loads in alternating current circuits. Some amount of inductance is present in all alternating current circuits because of the continually changing magnetic field. The amount of inductance in a single conductor is extremely small, and in most instances is not even considering the circuit calculations. Circuits are generally considered to contain inductance when any type of load that contains a coil is used. For circuits that contain a coil, inductance is considered in circuit calculations. Loads such as motors, transformers, line and ballast, and chokes all contain coils of wire. Whenever current flows through a coil of a wire, a magnetic field is created around the wire. If the amount of current decreases, the magnetic field collapses. When the magnetic lines of flux cut through a coil, a voltage is induced in the coil. An induced voltage is always opposite in polarity to the applied voltage. This is often referred to as counter EMF. The amount of induced voltage is proportional to the rate or change of current. An inductor opposes the change of current. Therefore, the magnetic field continually increases, decreases, and reverses polarity. Since the magnetic field continually changes magnitude in direction, a voltage is continually being induced in the coil. This induced voltage is 180 degrees out of phase with the applied voltage, and is always in opposition to the applied voltage. Since the induced voltage is always in opposition to the applied voltage, the applied voltage must overcome the induced voltage before current can flow through the circuit. For example, assume an inductor is connected to a 120 volts AC line. Now, assume that the inductor has an induced voltage of 116 volts AC. Since an equal amount of applied voltage must be used to overcome the induced voltage, there would be only about 4 volts to push current through the wire resistance of the coil. So how do we compute the induced voltage? The amount of induced voltage in an inductor can be computed if the resistance of the wire and the coil and the amount of circuit current are known. That's when we get to Ohm's law. For example, assume that an ohm meter is used to measure the actual amount of resistance in a coil. And the coil is found to contain 6 ohms of wire resistance. Now, assume that the coil is connected to a 120 volts AC circuit, and an ammeter measures a current flow of 0.8 amps. Ohm's law can now be used to determine the amount of voltage necessary to push 0.8 amps of current through 6 ohms of resistance. E, which stands for voltage, equals I times R. I stands for amps and R for resistance. So we said E equals I times R equals voltage, or E, 0.8 times 6, which gives us a total of E, or voltage, equals to 4.8 volts. Since only 4.8 volts is needed to push the current through the wire resistance of the inductor, the remainder of the 120 volts is used to overcome the coil's induced voltage of 119.9 volts. Inductive reactance. Notice that the induced voltage is able to limit the flow of current through the circuit in a manner similar to resistance. This induced voltage is not resistance, but it can limit the flow of current just as resistance does. This current limiting property of the inductor is called reactance, and is symbolized by the letter X. This reactance is caused by inductance, so it is called inductive reactance, and is symbolized by XL, pronounced X sub L. Inductive reactance is measured in ohms, just as resistance is, and can be computed when the values of inductance and frequency are known. The following formula can be used to find inductive reactance. X sub L equals 2 times pi times F times L. XL equals inductive reactance. 2 equals a constant. Pi equals 3.1416. F equals frequency in hertz. L stands for, or equals, inductance in henries. Inductive reactance is an induced voltage and is, therefore, proportional to the 3 factors that determine induced voltage: the number of turns of wire, strength of the magnetic field, and the speed of the cutting action relative motion between the inductor and the magnetic lines of flux. The numbers of turns of wire and strength of the magnetic field are determined by the physical construction of the inductor. Factors such as the size of the wire, the number of turns, how close the turns are to each other, and the type of core material determine the amount of inductance in Henrys, identified by the letter H. The speed of the current action is proportional to the frequency in hertz. An increase of frequency will cause the magnetic lines of flux to cut the conductors at a faster rate, and thus will produce a higher induced voltage or more inductive reactance. Inductors connected in series. When inductors are connected in series, the total inductance of the circuit, or LT total, equals the sum of the inductances of all the inductors. So, LT equals L1 plus L2 plus L3. The total inductive reactance, or X sub LT, of inductors connected in series equals the sum of the inductive reactances for all the inductors. The total inductive reactance, or X sub LT, of inductors connected in a series equals the sum of the inductive reactances for all the inductors. Therefore, the formula X sub LT equals X sub L1 plus X sub L2 plus X sub L3. Inductors connected in parallel. When inductors are connected in parallel, the total inductance can be found in a similar manner to finding the total resistance of a parallel circuit. The reciprocal of the total inductance is equal to the sum of the reciprocals of all the inductors. So, LT total equals 1 over L1 plus 1 over L2 plus 1 over L3. Therefore, LT total equals 1 over L1 plus 1 over L2 plus 1 over L3. In a pure inductive circuit, the current lags the voltage by 90 degrees. At first, this may seem to be an impossible condition until the relationship of the applied voltage and induced voltage is considered. How the current and applied voltage can become 90 degrees out of phase with each other can be best explained by comparing the relationship of the current and induced voltage. Recall that the induced voltage is proportional to the rate of change of current, the speed of current action. At the beginning of the waveform, the current is shown at its maximum value in the negative direction. At this time, the current is not changing, so induced voltage is 0. As the current begins to decrease in value, at this time the current is not changing, so induced voltage is 0. As the current begins to decrease in value, the magnetic field produced by the flow of current decreases or collapses and begins to induce a voltage into the coil as it cuts through the conductors. The greatest rate of current change occurs when the current passes from negative through zero and begins to increase in the positive direction. Since the current is changing at the greatest rate, the induced voltage is maximum. As current approaches its peak value in the positive direction, the rate of change decreases, causing a decrease in the induced voltage. In a pure resistive circuit, the true power, or watts, it's equal to the product of voltage and current. In a pure inductive circuit, however, no true power, or watts, is produced. Recall that voltage and current must both be either positive or negative before true power can be produced. Since the voltage and current are 90 degrees out of phase with each other, in a pure inductive circuit, the current and voltage will be at different polarities 50% of the time, and at the same polarity 50% of the time. During the period of time that current and voltage have the same polarity, power is being given to the circuit in the form of creating a magnetic field. When the current and voltage are opposite in polarity, power is being given back to the circuit as the magnetic field collapses and induces a voltage back into the circuit. Since power is stored in the form of a magnetic field and then given back, no power is used by the inductor. Any power used in an inductor is caused by losses such as the resistance of the wire used to construct the inductor, generally referred to as I square R losses, eddy currents, and hysteresis losses. Reactive power. Although essentially no true power is being used, except by previously mentioned losses, an electrical measurement called VARs is used to measure the reactive power. In a pure inductive circuit, VARs is an abbreviation for volt amps reactive. VARs can be computed in the same way as watts, except that the inductive values are substituted for resistive values. VARs is an abbreviation for volt amps reactive. VARs can be computed in the same way as watts, except that inductive values are substituted for resistive values in the formula. VARs is equal to the amount of current flowing through an inductive circuit times the voltage applied to the inductive part of the circuit. Several formulas for calculating VARs are: VARs equals EL times IL. EL stands for voltage applied to an inductor, and IL stands for current flow through an inductor. Therefore, VARs equals EL squared over XL. VARs equals IL squared times XL. So, the Q of an inductor Since inductors are actually coils of wire, they all contain some amount of internal resistance. Inductors actually appear to be a coil connecting in series with some amount of resistance. The amount of resistance compared with the inductive reactance determines the Q for coil. The letter Q stands for quality. Inductors that have a higher ratio of inductive reactance to resistance are considered to be inductors of higher quality. An inductor constructed with a large wire will have a no wire resistance and therefore a higher Q. Q can be calculated by the equation Q equals XL over R. All our inductors have some amount of resistance. Inductors that have a Q of 10 or greater are generally considered to be pure inductors. Once the ratio of inductive reactance becomes 10 times as great as resistance, the amount of resistance is considered negligible. For example, assume an inductor has an inductive reactance of 100 ohms and a wire resistance of 10 ohms. The inductive reactor component in the circuit is 90 degrees out of phase with the resistive component. This relationship produces a right triangle. The total current limiting effect of the inductor is a combination of the inductive reactance and resistance. The total current limiting effect is called impedance and is symbolized by the letter Z. The impedance of the circuit is represented by the hypotenuse of the right triangle formed by the inductive reactance and the resistance. To compute the value of impedance for the coil, the inductive reactance and resistance must be added. Since these two components from the legs of the right triangle and the impedance forms the hypotenuse, the Pythagorean theorem discussed before can be used to compute the value of impedance. Z equals square root of R squared plus XL squared. Z equals square root of 10 squared plus 100 squared. Z equals square root of 10,100. Z equals 100.5 ohms.
Thank you guys for watching, and if you like my videos, please like, share, and subscribe.